Okay, so I'm going to record lecture 13 on convolutional neural network, abbreviated as CNN or ConvNet. So the CNN was originally created to analyze the image type of data where we have this two-dimensional map where each square is a pixel and the value of this pixel indicate the intensity. And for image, there is a notion for translation invariant, that is a object can appear at any location for the image. So therefore, when we perform operations on the image, those operations should also be translation invariant, or it is like we are doing a sliding window and we perform the same operation within any window, within each window. So a 2D image is like a two-dimensional map, for example, 100 by 100. Later, we will come back to this 2D situation. But for now, let's start from this one-dimensional situation for simplicity. That is, we look at the 1D map. It's like one-dimensional image. You can also think of this as a time series. But in any case, suppose now we have d pixels in this one-dimensional map, okay? And then let input be x and output be y for this convolutional operation. So here, x and y are just two adjacent layers for the neural network. And they are not necessarily the raw input or raw output. So here we change the notation a little bit. So x is a certain layer and y is a layer above. And the y is computed from x. So for the multi-layer perceptron, without any like a translation invariant or shaped invariant constraint, then this x is a d-dimensional vector, y is a d-dimensional vector. And in order to compute y from x, we can multiply x by a d by d matrix, right? And then plus the d-dimensional bias vector, and then nonlinear ratification element-wise. So that's a common structure for multi-layer perceptron. But if we assume that the operations are translation invariant or shift invariant, then we can actually make the transformation simpler. So again, here both x and y are one-dimensional maps, and we use d to denote the size, and k, which range from 1 to d, to denote the position of a pixel. And in this operation, let's consider the simple example. So yk is a value at position k, and we perform the transformation. So yk equals w minus 1 times xk minus 1 plus w0 times xk plus w1 times xk plus 1. And we do this for all k. It's like you slide the window, right? But then the coefficients like w negative 1, w0, and w1 are all shared at all the positions k. So that is the weights. You see the weights are the same no matter what k is. Okay, and so we can write this this window w negative 1, w0, w1. So this is like a three pixel window, right? It's like you slide this window on this x, and then you perform this weighted sum, so you get y. And there may be an issue for boundary, so we just zero pad at the boundary. So that is we put a 0 here, we put a 0 here. So if your window is here, you get 0 times W negative 1, right? And if you are here, you have 0 times W1. Okay, if your window is here, you want to compute this value. This way, yk is defined for all the k from 1 to d. So that's the sliding window. And the reason we use this sliding window, this operation, so it's like we perform the same weighted sum operation at all the locations k, because W negative 1, W0, W1. So this window is shared by all the positions k. So we call this as a kernel or a filter. So you put a filter at different locations and positions, and then you use the same weighted summation of the 3 adjacent values to compute y. And after we get this linear combination, we can then add the bias term and also rectification. For example, ReLU, just like a regular neural network. However, unlike multi-layer perceptron, where the linear operation include a d by d matrix, right? This you multiply x by d matrix. But here you see we only need these 3 coefficients to translate x to y. So therefore, we use much less parameters, and this model use only a small fraction of the parameters of a multi-layer perceptron. And also, if you look at the connection, so here, this neuron or this node is only connected to these 3 nodes for x. And here, this one also just connect to 3 nodes of x. So this is a local connection. But for a multi-layer perceptron, a generic neural network, it is fully connected. So each neuron here is connected to all the neurons below. And also there's now shared weights. That is the connection weights, say W negative 1, W0, and W1. This is shared at all the positions. But for a so-called fully connected multi-layer perceptron, as we studied before, there's no shared weights whatsoever. Okay, so so therefore we can see that this type of convolution operation actually greatly reduce the number of parameters in this neural network by taking advantage of this shift invariant property of the image or 1D map. Because as I said before, so an object can appear at any location, and then in order to detect the object, you perform the same type of operations at all the different locations. Okay, so this is called the shared weights. So the weights is shared at all the locations, and here this kernel. So this kernel or this filter actually is illustrated by this connection weights, which are shared at all the locations. Okay, and so here we use a relatively small window, small filter. We can make the filter bigger, so that you see here we have W0, and we also extend to like W negative 3 and W3. And then if you look at the linear operation, so yk is W negative 3 xk minus 3, right, plus W negative 2 xk minus 2, and so on, until W0 xk, until x3 xk plus 3. For that to be defined for all the k, we need to pad more zeros at the boundary, okay, so that we can calculate this yk for all the k from 1 to d. Okay, so now let's move on to study a more complex situation, and which is more common in the convolutional neural network. So that is, again, x is an input and y is output. And again, so x and y are two adjacent layers in this neural network. So it's not like a raw input or raw output. So x may be layer 4, for example, and y is a layer 5. But in each layer, we may have the so-called channels, multiple channels. For example, y may have 3 channels and x may have 2 channels. Okay, in that case, how do we define this convolutional operation, this so-called convolutional layers? The way we do this actually is the same as what we did before in this one channel situation, right? In the previous page, we studied this one channel situation, and we can still use the same formula as in the one channel situation. So yk is w negative 1, xk minus 1, plus w0, xk plus w1, xk plus 1. But here we need to use the vector notation. So that is each for yk consists of yk1, yk2, yk3. So this is 3 by 1 vector. And yk1 belongs to the first channel, yk2 belongs to the second channel, yk3 belongs to the third channel. So that is, we now focus on this location, position k, and at position k, we have 3 y values, and we combine them into a vector. So this is 3 by 1 vector. Similarly, xk, which consists of xk1, xk2, this become a 2 by 1 vector. And then if we continue to use the same formula as in the case for one channel situation, then this is 3 by 1, right? And this 2 by 1. And then this W, all those W should be matrices, in particular 3 by 2 matrices, so that if we multiply this matrix to this vector, we're going to get a 3 by 1 vector. And we sum them over, we get this 3 by 1 vector. So that is now, you see that again, we introduce the vector notation, but this time we have a vector defined at each position. At each position, we have a vector. Okay, and again, we can think of this as a sort vector, right? How do you think about this position? What do you see at this position? So this can be considered as describing or representing a sort of what you see or what the pattern that you see. Okay, and then using the same formula, but now generalizing y and x to vectors and generalizing the w to matrices, we then get this more general definition for convolution, the linear part of the convolution. Okay, so therefore you see w negative 1 is 3 by 2 matrix, right? And the xk minus 1 is 2 by 1 vector. And similarly, w0, xk, w plus 1, xk plus 1. So now we have all those vector matrix notation. So this type of vector notation is very useful for us to understand neural network. So that is at these 2 layers, right? We have multiple vectors. At each layer, we have a vector defined at each position. So each layer consists of all those vectors. And then for the layer y, this vector is computed by combining this vector and this vector and this vector. Okay, so that's how we think about it. It is like we have a team of vectors, and we position those vectors at different positions at each layer. And we call those layers as a convolutional layer because they are obtained by the convolution operation like this one. Okay, and so this is one way to look at it. But another way is through this direction, through this horizontal direction instead of vertical direction, so that each channel is actually a map, right? So we have two channels. We have three channels here, so we have three maps. And we have two channels here, we have two maps. This is another way to think about it. I think in traditional introduction for CNN or ConvNet, people often focus on this feature map type of representation. But I believe that this vector representation is simpler and also perhaps can go further, because later we will see recurrent neural network and the transformer. They are all about vectors. Sometimes people also call the vectors as a code or a embedding. Okay. And then later we can also add the bias vector, right? And then add the retification. So the retification always applied element-wise, always one-dimensional. For example, sigmoid or ReLU. Okay, so that's the basic operation for convolution. With the above preparation, we are now ready to come back to the two-dimensional situation, which is a main scenario for applying convolutional neural network. So again, we need to generalize the formula to 2D, and then we define the sliding window in 2D. So again, let's start from this one channel situation. So suppose this is our X. Now X is a two-dimensional map, and then we have Y, and X and Y are again of the same shape, same size. But this time we have IJ to index the pixel or position. So in the 1D situation, we use K, right? K from 1 to D. And now we use IJ to denote the position. And then again, we can use a kernel or filter. For example, is 3 by 3 filter as our W. And then we slide this this filter over the image with again zero padding, so that we can calculate Yij. In particular, Yij is W -1 times Xi minus 1 J minus 1, and then plus W -1 0, this W value, this weight here times this value, and this one times this one, this one times this one. So you just multiply those things and add them up, you get Yij. So therefore, you see each Yij is a combination of these 3 by 3 values, a linear combination of the 3 by 3 values, and its coefficients are the same no matter what Ij is. So you can slide this window at different places, centered at different Ij, but the linear weights are always the same. So this is essentially the same as a one-dimensional situation. So we are just generalizing one-dimensional situation to a two-dimensional situation. Certainly, you can also generalize this to 3D, right? For example, for video, you have spatial and the temporal dimension, that's a 3D. Or if you study some like a 3D type of shape, you can also use this 3D convolution. But most commonly, we use CNN for computer vision, and we have this 2D type of kernel. Okay. Now let me continue. I think it's the previous page. Moving up. Sorry about that. Okay, so somehow let's move up, please. Okay, how do I move up? My scroller doesn't work now. Let me exit. Okay, I think in this page. Okay, good. So let me get down to the full screen mode. Okay, good. So now we, I think I need to. So that's the problem with the screen mode. Oops, sorry about that. I think my trackpad is not responsive, very responsive. Okay, I move slowly to here. Okay, so again, we can make the filter bigger, for example, 5 by 5 or 7 by 7. Okay, so now we can continue to generalize this to multiple channels, just like what we did for the one-dimensional situation. And for multiple channels, we draw the picture in this way. So we use a 3D plot. So this is one channel. For example, this is 100 by 100 map. And then we have, suppose we have 10 channels in X. This is our X. And then we have maybe 20 channels in Y. But for each channel, the shape is the same as the channel, each channel in X. For example, this is also 100 by 100. Okay. And so we use this, again, we continue to use ij to denote the position. And this time, just like what we did for the 1D situation, so xij now becomes a vector, right? And yij is also a vector. So because we have 10 channels in X, so at each ij, so xij consists of the features at these 10 channels. So this is a 10-dimensional vector. And for yij, we have 20 channels. So this is 20-dimensional vector. Okay. And how this vector is computed? Actually, we can use this formula. So yij is computed as a summation for we use delta I to denote the possible shift. So the shift can be -1, 0, and 1. And the delta J is a shift which can be -1, 0, or 1. Okay, so this is a shift. And then this gives us a 3 by 3 shift, right? 3 by 3 kernel. And then we have W delta I delta J, and then times X I plus delta I and J plus delta J. So this is a simple formula. And you can go back to the previous page, like here. So essentially, this is what we have. So Yij, we now use the summation notation instead of writing out all those things. So it's a double sum, right? The summation delta I can be from -1 to 0 to 1, and delta J can be again -1, 0, and 1. So in total, we have 3 by 3, right? And this each one is delta I delta J. So you see delta I delta J here is -1, -1, and delta I delta J here is 1 and 1. And for each shift, you have a W, say W -1, -1, and W W1, 1. Okay, and then you sum them over. And at the same time, you also shift I and j here. So this I plus delta I and j plus delta j. So we just write this formula in more concise form into this formula. Okay, so that is Yij equals summation. So delta I is from -1 to 1 and delta j from -1 to 1. This gives us this 3 by 3 kernel. So this negative delta I, right? You see delta I can be from -1 to 1. Delta j can be from -1 to 1. So we have this 3 by 3 kernel. And for each delta I, delta j, we have W, right? And then we can write it in this way. So this is certainly true for one channel situation where all those things are numbers. And in the multi-channel situation, then this Yij become a 20-dimensional vector and Xij become a 10-dimensional vector, depending on how many channels we have, right? And then again, we have the shape of I and j. So this gives us 3 by 3 kernel, okay, our filter. And then we have W delta I delta j for 3 by 3 within this 3 by 3 range. And then X I plus delta I, j plus delta j. So that is here. At Ij, you have one vector, and then you shift this, right? So you have 3 by 3 window, and then you have 9 vectors. So here Yij is actually a linear combination of these 9 vectors. And if we plot this, so this is a 20-dimensional vector, and this equal to the summation over this window, 3 by 3 window, so that and then we have this matrix. This is a 20 by 10, so this is 10-dimensional. I think the drawing is a little bit out of proportion. This should be a longer longer vector, and this is shorter actually. This is 20-dimensional. This is 10-dimensional. And then this is a 20 by 10, right? 20 by 10. And then we sum them over. You see, we actually linearly combine 3 by 3, which is 9 vectors. Okay, so this is 10-dimensional vector. If we multiply this 10-dimensional vector by a 20 by 10 matrix in front, we get a 20-dimensional vector. And then we add them up, we get this 20-dimensional vector. We can also add a bias, which is also 20-dimensional, and then plus ReLU rectification or sigmoid rectification. Okay, so that's the basic idea. So basically, Yij is a vector that is a composition for the 9 vectors in this X layer. And each value of this vector corresponds to a channel. Okay. Again, here you see we look at this convolution more from the perspective of the vector at each position instead of for the map, the feature map for each channel. Because again, this vector is a more useful way or perspective to think about the neural network. Again, here you position all those vectors at different positions, right? And these vectors at different positions, and then they supposedly pass message to each other. So it is like you have this X, and then this W extracts some message from this this X vector, and then this you combine all those messages and then send it to this Y. Okay, so that's the way we think about it. And again, you can think of each vector as representing a thought, because each vector consists of multiple neurons. So here you have 20 neurons. Their activities form a thought. So we call this as a thought vector. So how do you think about this local pattern, what you see, right? And this sort is a composition of 9 sort vectors at the layer below. So you keep composing the vectors so that you see bigger and bigger pattern, and also you see more and more complex pattern. So that's the basic idea. So you can think of each vector as entity, as a noun, right? And then each matrix, the matrix is like a verb or operator. It operates on this noun to perform some transformation or extract some message or some thought, and then you add them up. So this is composition, spatial composition. You're composing all the vectors in this window and to form a bigger vector or a more complex thought. Okay, so that's this vector perspective for convolutional neural network. Of course, you can also view this from the channel perspective, because each dimension or each element of the vector corresponds to the feature for this channel, the map, right, at this position. And then if you look at each feature, okay, for example, the value here, it is actually computed again a spatial composition, which is this row vector in this weight matrix multiplied by this vector. So, and then you add them up. So that is this each value here is again a linear combination for the 9 vectors here. So for each vector, you multiply this by a weight vector, so that this inner product become a number, right? And you add up the 9 numbers. So that is again, each number here, each feature here at each channel. So this is a linear combination for these 9 vectors here. And it is computed by this row vector multiplied by this column vector, and then you sum them over. More specifically, you can also think of, this each this row vector, you are doing some composition. So this one is computed again from this. So in this summation, right? In this summation, so this one is computed by linearly sum over these 9 values, okay, on this channel. And then for another channel, you also have 9 values. You linearly sum them over, and then you add up all the channels, all this all the 10 channels. Okay, you can also think in this way. So there are many different ways for parsing this vector matrix notation. Okay, so that for each one, you have this 3 by 3, okay, 3 by 3 summation, and so that is this number is a linear combination of these 3 by 3 numbers plus a linear combination of the 3 by 3 numbers in another channel, linear combinations of 3 by 3 numbers in another channel, and then you add up all the channels. Okay, so you can also think in this way. But still, I feel that the easiest way to write this convolution is to use this vector matrix notation. And also just think about the vectors at different positions. This is good enough for you to understand. So that is our perspective. It's a little bit different from those introductions that you can find online. We focus on the thought vector. So this thought vector is a spatial composition for the thought vectors at the layer below after this type of transformation. And also this vector notation make it simple, easier to think about this so-called one-by-one convolution. In this one-by-one convolution, we do not have spatial extent. so that this vector Yij is not a composition of these 9 vectors. This vector Yij, is only transformed from the vector Xij, no spatial composition whatsoever. And in particular, so this Yij is simply just W00 times Xij. You can also add a bias and the ReLU. Okay, so this is so-called one-by-one convolution. So in other words, the kernel is only one by one without any spatial extent. So what we are doing here is basically just to combine the channels, okay, and without pulling the spatial information. So this way you can either expand the number of channels, in this case from 10 to 20, but you can also reduce the number of channels, for example, from 10 to 5. And you can also think that at each position ij, right, at each position, you are actually performing, this is similar to a multi-layer perceptron, right? You do multi-layer perceptron. So you have this vector and multiplied by, which is obtained by this vector multiplied by this matrix. So that is at each position, you have a like a multi-layer perceptron type of operation. And sometimes this is also called a network within the network. Okay. So now let me move to the next page. Okay, my trackpad hopefully can work. Okay, so we get to the next page. Okay, good, it works. So after this convolutional operation, we can then also perform subsampling. Okay. Okay, here. So for subsample, we suppose we have this map, right? And we just want to make our map smaller. The reason is that the adjacent or nearby y vectors, they are computed from the overlapping windows, right? Overlapping 3x3 windows. So that may be too redundant. And if you keep them, the computation may be too excessive, and it may also cause some overfitting. So therefore, we want to perform subsampling after convolution. For example, this is a 4x4 map, right? We can reduce this to 2x2 by subsample with a so-called strat 2. So we take one value every 2x2 block, and then we reduce this into 2x2. Sometimes we can also perform the so-called max pooling. That is, within each 2x2 block, we choose a maximum value, and we put it here. And this one, we choose maximum value, put it here. We can also do max pooling. And for this type of subsampling, this is called a strat. So the strat equals 2. So you you keep 1 pixel every 2 pixels along each dimension, along each direction. So that's the basic idea. And usually after you do this convolution, the subsample is just done in this way. But in some modern design of the neural network, people actually use a 2x2 kernel, 2x2 filter to do the reduction. So you have 2x2 filter applied to this part, and then you get this value. And another, the same 2x2 filter, but at this location, you get this value. So this is overlapping 2x2 filters, you get this one. So you can use a particular layer, 2x2 filters with strat 2 to perform the subsample. This is also okay. And then we can now fit everything together to see a typical convolutional neural network as a whole. So suppose the input is an image. Actually, the input, a color image has 3 channels, RGB, right? Because color can be decomposed into RGB, red, green, and blue. And so this is 3 channels, and the map is 100 by 100. And then we perform the convolution. We may have, for example, 16 channels and still 100 by 100. And with all those convolution, like a spatial composition plus bias plus ReLU. So we got this this layer, and then we perform subsample to make the 50 by 50, like what we do here. And then we continue to do the convolution. Okay, for this convolution, we then get to this one. So maybe we make bigger. So it's 128 channels and 50 by 50. And again, we do subsample. So we still have 128 channels, but the map become 25 by 25 after this subsample. Okay, and then continue eventually. After the subsample, keep doing the subsample, you are going to get a just one-dimensional or 1 by 1. So the map become 1 by 1. When the map become 1 by 1, then you have this a single vector. Okay, so for at the convolutional layer, you have multiple vectors, or you have one vector at each position, right? But at this point, when the map become 1 by 1, you have a single vector representing the whole image. And suppose you just get this like a 4,000 dimensional vector from this map, then this one is computed by a linear combination of all the 25 by 25 vectors. Or in other words, this one is a linear combination of all the values in this layer. Okay. So now we get a vector. This is like a 1 by 1 by 4,000 vector. And this is just a vector. And then we treat this as a multi-layer perceptron, right? For the rest, it's like a multi-layer perceptron. It becomes fully connected. And then we get another, say, 4,000 dimensional vector. Here, this connection weight will be a matrix, which is 4,000 by 4,000. Later, people stop using this design because it costs too much of the parameters, number parameters. Okay, so after that layer, you can continue just like a classification. Finally, you generate this, for example, 1,000 logic scores. And this gives you 1,000 probabilities. So the dimension of this one should be the same as this one. So you get 1,000 probabilities after softmax. Okay, and then you can make classification. So this is the full picture for a CNN or ConvNet. So in the beginning, you have this the so-called convolutional layers. You perform this convolution and subsample, and in the end, you just have 1 by 1 like a map, so that you have this vector, and then this part is like a multi-layer perceptron, typical multi-layer perceptron, and until you get this logic score, and after softmax, you get the class probabilities. Okay, so to make prediction. So this part is called fully connected layers. And then when you train the neural network, you can just follow the method we studied before. So for the classification, you use this so-called negative log likelihood, right? Or the cross entropy loss, where the derivative of the cross entropy loss or negative log likelihood with respect to the to this top layer logic scores will be just negative y minus p. Y is 1/2. Suppose you have 1,000 categories. So y is 1/2 vector of 1,000 dimensional, and p is a vector 1,000 dimensional probabilities. So the probabilities of this 1,000 categories, which sum to 1. So the difference is error. And then you do error by propagation. So this part, because of the convolutional layer, when you do the backpropagation, you need to take some special care that the weight are shared. So you need to sum over all the positions in this backpropagation, because the same set of weights is applied at all the positions. Okay, but still the principle is like you do backpropagation using the chain rule, right? And in this way, you can continue to use gradient descent or Adam algorithm to learn all those weights and the bias parameters in this convolutional layer, as well as the weight matrices and the bias parameters in this fully connected layer. And then you train a neural network. So in the ImageNet, they have, for example, 1,000 categories. So here, this is 1,000. And then you have this 1 million images. And then you can train this neural network on this data set. And then you can learn to classify the images into different categories. For example, cat or dog and so on. Okay, so that's the basic idea for convolutional neural network. And after you train on the ImageNet dataset, those ways enable you to compute for each image those layers. So those layers, you have those features, right? And those features can be used for other purposes, for example, for downstream tasks. So therefore, the point for this convolutional neural network is that you do not need to design features. The features are actually learned. And for example, at this first stage, so those vectors at different positions, they may detect edges at different orientations. So each channel take care of one particular orientation, and you detect edges at the different orientations. And then the next stage, you keep composing, right? Composing those edges. So you can see like eyes or mouth or nose and so on. And you keep composing. And here you may see a face. So this is a thought vector about the face. And then you use a fully connected layer to finally make classification, right? And to decide what object it is. Okay. So in terms of the vectors, we can also plot a convolutional neural network in this way. So originally we have image, right? At the first layer, we have the thought vectors that are 16-dimensional. And then we do convolution, we get 128-dimensional. So each thought vector here is a composition, spatial composition for some nearby vectors at this layer. Okay, because of the spatial composition, you see bigger pattern and the more complex pattern. That's why you use higher dimensional vector to represent the pattern. And then you keep going, you get higher and higher dimensional vectors. But along the way, because the nearby vectors, they are basically see very similar things. So you do subsample, you get rid of some vectors, you only keep those vectors with a bigger spatial separation, right? So that you have a less vectors, but each vector is of a higher dimension. And you keep doing that so that eventually the whole image, for this whole image, you only have a single high dimensional thought vector to think about this whole image. And then you go through several rounds for multi-layer perceptron, and then you make classification. So this is a plot from the perspective for thought vectors. So it is like a team of vectors. You position those vectors at different positions, and then you let those vectors to pass message from bottom to the top until you are able to make classification. And again, for each vector, at ij, say yij, is a spatial composition for the vectors nearby, so with a certain spatial extent. Okay, and this is how you do the composition. And because of the composition, so there's a lot of redundancy. So we do subsampling. So we get rid of some vectors so that they are more sparsely located. Okay, and this even sparser. And in the end, you only need a single vector to represent the whole image. Okay, so you learn those sort vectors for the purpose of making the classification. Eventually you get 1000 dimensional logic score. So you use the backpropagation to tune the weights so that you can compute those vectors from the input image. Supposedly, those vectors should capture more and more complex pattern, but more and more abstract pattern. So you throw away irrelevant information. You only keep the information that enable you to make classification. Okay, so therefore, if you go to the higher layers, and then those vectors are more about the category information, less about the original image information. So that is throw away those nuisance information, irrelevant information. Only keep the most essential information for the final purpose, whatever it is. For example, in this case, is to make classification. So in that sense, the vectors also become more and more abstract. So it is very possible that if you train this neural network, keep training, in the end, for each category, this logic vector may be centered around a centroid of this category. So they get very close to each other because you throw away the information about the image. You only keep the information about the category. Okay, so that's a possibility. And also, as I mentioned, so each layer you see bigger and bigger pattern. So here at each position, so this is a vector about the edges of different locations. So each dimension of each element of this vector may indicate whether you see an edge at a particular orientation. So each dimension may correspond to a particular orientation. And here, this one is composition for the vectors below. So you see a bigger pattern. You may see a corner or a circle or a curve or edge, a eye or nose and so on. And here you may see a more complex pattern. Okay, so that's you see bigger and bigger pattern, and at the same time, more and more abstract patterns. So that is you may throw away some unnecessary, irrelevant information that are not useful for your task. So as I mentioned before, after you train this neural network on ImageNet or some other big data set, you can store the learned weights, and then you should be able to apply the learned weights to a new image to extract the features. And you can either use vectors in this layer or vectors in this layer for downstream tasks. So this is so-called pre-training. So you pre-train a network on this big data set, and then you can keep the trained weights and then calculate those vectors. So this is like a feature extractor. So you learn how to extract features. And even though we train the neural network for make prediction, right, or classification, but those features may also be used for other purposes. And for the downstream task, if you only have a small data set, for example, the customer wants you to classify a new type of objects, whether it is a new type of object, and then you can still use those vectors and then or this vector to make classification, you only need to learn the final layer of weights. You can freeze the weights as in the trained model for the previous layers. So this way, you can easily transfer the model to some other tasks for the matter of pre-training. Okay, I think that's about it for this lecture. I can stop here.